Hello, so in this video I'm going to talk about integration by parts. Now, integration by parts starts by looking at the derivative of two functions, say f times g, and then we just say that we're going to take the derivative. So we know that the derivative of this equation would be f prime times g plus f times g prime. Now, interestingly enough, if we choose, for instance, that u is equal to f and v is equal to g, well, that means that the equation is actually u, v, take the derivative of that, and then this will equal to, okay, so we have v du. Now, all I'm doing is I'm just moving these to this to the front and this to the back, or just like reordering it. So I have then that this is going to be plus, okay, so this is going to be u and then dv. Okay, so the thing about this is that we can actually undo potentially the product rule. So we do that by integrating on both sides. Now if we do that, that gives us the following. It gives us uv minus, we're going to move this over here, so that's going to be minus the integral of v du, and this is equal to the integral of u dv. Now typically it should be the other way around, but you know, it's the same thing. Okay, so we have our formula. Okay, so this is our formula, and the question would become, you know, for instance, like how do you know which one is which whenever you're looking at a integral like u dv? Now, the way of which that we can decide, for instance, like how we can use our formula is kind of by using the following. It's what we call liat. Liat essentially determines what your u is and what your dv is. So, for instance, we have that this is going to be, so to determine u, we say that u is the most left for here, so this would be u. And as we move closer to the right side, this would be our dv. Now, it should be a question as to what is LIATE. L stands for our logarithmic equations. I stands for our inverse equations. A stands for algebraic expressions. T stands for our trigonometric equations. And then E stands for our exponential equations. Now, let's say, for example, that we want to use the formula. So let's say that we have the following integral. Find the integral of x e to the x dx. So accordingly, we know that u would have to be the most left of the algebraic expression and the exponential. So then u is equal to x du is equal to dx. dv is equal to e to the x dx. So that means that u is equal to e to the x. Now, what that means is that we basically just say that the integral e to the x, or x e to the x dx, is equal to x e to the x minus the integral of, let's see, this should be v, right? So that's a v. That's not a very nice v, so we'll just rewrite it. So v is equal to e to the x. So that's minus e to the x du, which is dx. So that becomes x e to the x minus e to the x, and that's going to be plus c. Potentially the plus c will come out of the last integral v du. Okay, so we have our solution as follows: x e to the x minus e to the x. Now if you want to get clever and say, for instance, like factor out the e to the x, you can. Okay, so let's say that we go ahead and we try to apply integration by parts again. So let's say, for example, that we have, okay, so we want to find the integral of the natural log of x dx. Now, if we go back to our little diagram right here, we have that the log would have to be the u. Now, that means that essentially that dv is actually just x. So we already know, like, okay, so u is equal to natural log of x, and du is equal to 1 over x dx. dv is actually just dx, which means that v is equal to x. So this tells us that we have x ln of x minus the integral of v du, which is just going to be, right, so that's going to be x multiplied by 1 over x dx. So this is our integral, and we have that this is going to be equal to, okay, so that's going to be minus the integral of 1 dx. Well, that's actually pretty easy because that's telling us that that's going to be natural log of x minus x, and then that's going to be, let's see, x ln of x. Oops. Okay, so this is going to be plus c. So that's our answer there for the integral of natural log. Now, I do have another way to apply the integration by parts, and that's given by the tabular method. Now, tabular method basically just requires making a diagram, essentially, on like how we can do, like, for instance, like multiple layers of integration. So the best way of kind of explaining it essentially is by demonstrating it with an example. Let's say, for instance, that we looked at the integral of x e to the x again. Now, we would still go about finding that u is equal to x and that dv is equal to e to the x. The only difference is that I would basically just make a table where I have a column where u will go and where not sorry, where dv will go. So in this column, we're actually taking x and we're going to differentiate it until it zeroes out. Now, in this column, we have e to the x, where we just take the antiderivative each time. But each of these layers start with a positive and then a negative and then a positive. What happens next is that we just go ahead and draw a little line like this and like that, and then we just go across to account for the c. So accordingly, this is going to be equal to x e to the x minus e to the x, and that's going to be plus c. And that's it. So see, like, how I didn't do anything with regard to the u aside to just saying u is x and dv is e to the x. So essentially, I'm actually taking care of the integration by parts in potentially like layers, but notice that this is just one layer. So tabular method is good for multiple layers in that case. Now let me try another example. For instance, like for if we have like the integral of x squared e to the x and dx. Well, this is actually the same thing essentially. You have that u is equal to x squared, and then dv is equal to e to the x. Okay, so what this means is that we have that we can make our table. So we make our table, and we have that this is going to be as follows. So we have x squared, 2x, 2, followed by a 0, followed by e to the x, e to the x, e to the x, and then e to the x. But remember, it starts with a plus, then minus, then plus, and then minus. So we go ahead and we formulate our layers. So that goes to that, that goes to that, that goes to that, and then it goes across. So what that means is that the solution is x squared e to the x minus 2x e to the x, and then plus 2 e to the x, and then that's plus c. And that's it. So I have that was very easy. And notice that there's multiple layers essentially. You have that the layer started after the second integration by parts. Okay, so that avoided having to do that. Now, I can furthermore try another example where we use the tabular method. So for instance, let's say that we want to find the integral of x ln of x dx. Well, I know that, I have my columns, and I know that I just need to pick my u, which in this case, u will be x, and then, actually, it's backwards. It's going to be that u is natural log of x, and dv is going to have to be x. So we have natural log of x, and then we have x. So this is going to be 1 over x, then this is going to be negative 1 over x squared. This is going to be x squared divided by 2. And then this is going to be, it's very likely that we didn't even need to do this third layer, but it's okay. It gives us some practice. So we have that this would be, let's see, 3x cubed over 6. Okay, but remember that we have a plus and a minus. So we have that this would be a plus, that'll be a minus, and that'll be a plus. So notice that it doesn't really cancel out essentially, and I think that one layer actually was enough. Okay, so, or 2 layers. So we have this, and then we have this, and then, well, actually it looks like we should have just went this way. So let's go ahead and just say that we only needed this second layer because it's u minus v du. So what this does is it tells me that I have that the solution is x squared over 2 times natural log of x minus, okay, so this is where it gets a little complicated because we didn't finish technically. So we have minus the v du, so that'll be 1 over x multiplied by x squared over 2, and that's du. Now what this does is it eliminates the x, so it's just x halves. So x squared ln of x minus the integral of x over 2 du, which of course this is equal to x squared natural log of x minus 1/4 x squared. And all of this is going to be plus c. Okay, So in this case, like we knew that essentially the ln of x was never going to cancel out ever. So in actuality, I guess like yeah, I should have realized that right about this layer, I should have said just stop because that's where it starts to cycle, and you don't want that when it starts to basically cycle. Um, which in this case, like yeah, that's probably what was about to happen was that it was going to start cycling itself. um, okay, so we can actually look at a different formula. Yes, so that should be divided by 2. Okay, so not only do we know that we need to know when to stop, um, yeah, but we have to remember not to forget about these constants. So we have x squared over 2. Okay. Now, the last thing that I will talk about, well, in terms of finding integrals, integration by parts, is I want to demonstrate, for instance, like how we can use integration by parts for when we're looking for a definite integral. So, for instance, let's say that you have the integral of 6x plus 7. Let's go ahead and rewrite that just a little bit just so that it's nice. Okay, so we have the integral of 6x plus 7, and then that's going to be e to the negative x, and this is from 0 to 1. Now note that we can try to implement a u substitution, but it's going to get a little more complicated, so I'd rather just avoid that. So let's say that we're just trying to find the area that corresponds to this. So we just have to pick our u. So u would be 6x plus 7. du, or not du, but dv is equal to e to the negative x. So what that does is it tells me that when I set up my table, I have that the first layer is 6x plus 7. The second layer is 6, then 0. This will be e to the negative x, which is negative e to the negative x, followed by e to the negative x. Now I know that there's going to be an alternating in the sign, so plus, negative, plus, and that from there we're just going to go like that and like this. Okay, so that means that we just need to do 2 layers essentially, which, okay, that comes out nicely to the following. Let's just say that this is equal to, okay, so note that we're not integrating anymore because that table accounted for it. So that's going to be negative 6x plus 7 multiplied by e to the negative x, evaluated from 0 to 1, and then that's going to be another negative because, yeah, it says minus, so that's going to be minus 6e to the negative x from 0 to 1. Now, what we have here is that when we plug in 1, we get negative 13 e to the negative 1. So that's going to be negative 13 e to the negative 1 plus 7e to the 0. So plus 7e to the 0 minus 6e to the negative 1, followed by plus 6e to the 0. Now, all of this can be computed easily by using a calculator, of which, take a moment to use your calculator. Okay, so if you go ahead and do that, you should get that the following answer is going to be, should be 6.01. So we have, that's going to be 6.01 as the answer for the definite integral. And of course, there should be like a dx over here. Okay. Now, last but not least, let's say, for example, that I want to use basically kind of like a formula to find my integral. So, for instance, there is a formula technically that you can derive for many different types of integration by parts problems, but unfortunately, we don't really deal with too many, at least in this class. So, for instance, let's say that we have x to the n and then e to the x dx. Now, according to tabular method, it would tell you that u is equal to x to the n and that dv is equal to e to the x. So what that means is that basically you have your column stated as follows. So the idea is that the integral will be based on a formula. So you have nx to the n minus 1, and then you have e to the x, and then e to the x. Now potentially this formula, it's basically just accounting for the first layer, because essentially you have that the whole process is kind of like iterative, which means that you just do it over and over again. So for instance, if we go ahead and we try to use the formula, well, we need the formula, right? So x to the n e to the x dx equals to x to the n e to the x minus n, n, the integral of x to the n minus 1 e to the x dx. Okay, so this is kind of like a formula that can be used to any integral of the form xn e to the x dx. So that means that I can use this formula for any integral raised to any single power. But notice that it's e of x, not e of 2x and so on. So that means that it might get complicated if it's like x cubed e to the 3x, because it's not in the format that you see above. So let's say that we have the integral of, let's say like you have x squared e to the x dx. According to the formula, it says that n is equal to 2. So that's going to be x squared e to the x minus 2, the integral of x to the 1, and then you have e to the x dx. Now, we technically already know, for instance, what the integral of x to the ex is, but we can do that again using the formula. You have x squared e to the x minus 2 parentheses. Okay, so if we use this again, we have e to the x times x, so we'll just put an x right there, minus the integral of x to the 0 e to the x dx, close parentheses. Now if we go ahead and we simplify this, basically we end up getting x squared e to the x minus 2x e to the x plus 2 e to the x, and then plus c because of that last integral. So I did all of the work without, or I did the integral of x squared e to the x without doing too much work, essentially, because I just used a formula. Now you do have other formulas or tables that you will use in your homework, but more or less you should be able to get the idea of how I used it in this example.